So in an earlier lesson, we got to see that the derivative of exponential functions base e is a very unique function, that the derivative of e to the x is e to the x. But we never talked about other bases. And the question, of course, is would it work so well for other base exponential functions? And unfortunately, the answer is not quite as nice. But the chain rule is going to give us a way to verify or to establish what the derivative of exponential functions of any base are. But remember that an exponential function is of the form f of x equals a to the x, where a has to be some positive number and not equal to 1. So the not equal to 1, I hope should be fairly obvious, from having done these in pre-calculus. 1 to any power is always 1. So it's kind of boring because it's just a constant function. Otherwise, though, the base has to be positive because when you start looking at fraction powers, you run into problems if you have a negative base and you're trying to do, say, a 1/2 power. So we run into a whole bunch of problems. Actually, now that we've been through a little bit of calculus, continuity and whatnot, we can talk about how the reason a can't be negative is because you get a function that is discontinuous at all input values, which is kind of weird. It's literally not continuous anywhere. So, something we'd rather avoid. It's nice if we have 1 or 2 discontinuities, that's manageable, but we don't want to have literally the entire graph be discontinuous. So, we keep a being positive. Now, I want to consider this function. Now, e certainly fits the requirements that it is positive and not equal to 1. But here's what we need to realize is that the output value of any exponential function is always positive. Now, here's the sneaky part. The output of an exponential is always positive, and the base of an exponential must always be positive. These are actually saying the same thing. What that means is that for every imaginable base you can think of, there is some power of e that gets there. This fact right here is what we need in order to be able to do the derivative of any exponential function. The idea that for any value a that is positive, there is some value k such that e to the k equals a. We've got e to a power, which always produces a positive number, and a, which could be any positive number. So this is any positive number, that's any positive number. There's got to be a value, some power of e somewhere, that makes these e to that power and a equal to each other. So that's going to be the key here. Because what we can now say is that if this is true, then we can replace a with e to the k. And the advantage here is, as we've seen with other things that we've done through the semester, the advantage here is that we've got a to the x, a new function, written in terms of a function we are already familiar with, that we've already proven. Now we can do one more thing to clean this up, and that is to multiply the exponents. This is a property of exponents. And you can see perhaps why the chain rule is going to be necessary to differentiate this, because we have an inside function. A simple inside function, but we do have one. So that's the key here, that for any base of an exponential function that we could possibly have, there is some power of e that is equivalent to it. So therefore, the derivative of a to the x, since we don't know how to do that, we will instead use e to the x, or e to the kx rather, an equivalent form that is better suited to what we're going to do. So again, we're going to employ the chain rule by taking the expression in the exponent and making that our u. So we need our du dx, our derivative of the inside function. Now, the thing to remember here is that a, for any exponential function, a is a known constant. It's a known value, which means k must also be fixed because e is fixed. So if a is a constant and e is a constant, k has to also be a constant. And what we've got here is a linear function whose derivative is the coefficient of x, k. And of course, the derivative of e to the u is e to the u. Well, times du dx. So, we have the derivative with respect to x of e to the kx is equal to e to the u times du dx. We're going to rewrite it in terms of the original variable. And we have k e to the kx. Well, another step here, much like what we saw with the proof of the power rule, we are now going to take this and return it back to its original form. So e to the kx has the equivalent form of a to the x. We're only left with one question. What on earth is the value of k? Well, the value of k, if a and e are both known, then certainly we could figure out the value of k. So we've got the relationship that a is equal to e to the k. Well, if we want to solve this for k, we need a natural log on both sides. But of course, the natural log of e to a power cancels out and leaves us with just the power. So k is the natural log of a. So when all is said and done, the derivative of a to the x is the natural log of a times a to the x. So not tremendously dissimilar. I mean, the derivative of this exponential function is still the same exponential function, much like the derivative of e to the u is e to the u, but we have to multiply by the natural log of the base. So a slight extra little bit there, but not all that dissimilar from the e to the x derivative. But again, the chain rule saw us through this. Now, that does raise the question of what about logarithms with other bases? And that comes in the next video.